Alright, now we will continue our discussion regarding the fluid motion. And in this video, we will be deriving the equations that would express the relationship between the pressure, the elevation, and then the velocity. Okay, so now let's consider an element. Okay, and then this is our fluid element. And this is the path, or I guess this should be the streamline. And let's say we are going to use the path coordinate systems. Okay. Instead of using the XYZ, or I mean the rectangular coordinate systems, we'll rather use the path coordinate systems. And we have also discussed this in our course in dynamics. So for the path coordinate systems, we have an axis along the streamline. So that's always along the streamline. And then we have another axis that's normal to the streamline. Okay, so let's now expose the forces. We have this force, a pressure force. Let's say this is P, the pressure P times the area to which it is acting. If we try to draw this in three-dimensional view, this would be like this. And this is our streamline. And this is our force, which is just simply equal to the pressure times the differential area. So this differential area is actually the area perpendicular to the pressure force. Okay, so we have a pressure times the area in this side, and at the other side we'll also have a pressure, except that let's say P plus the, should there be any changes or difference in the pressure, that's P plus dP times the area, differential area. Okay, and we'll also have the weight of the fluid element, and with respect to this axis, then of course we'll have an angle right here. It's actually we will also experience forces along the normal, except that for now we'll only derive the equations, the let's say an expression regarding or along the streamline. Okay, so you can have actually pressure forces along the normal axis. And we'll also have a relationship regarding this. So this is our, if this is our S, right? If this is our S, then this will be our Z, and then this will be our X, and this will be our theta. Okay, so now let's write the forces acting along the path. Would be the PDA, right, and the P plus D, this force, P plus dP times dA plus the this one. Alright, so the S component, it's the S component of the weight, which is W sine theta. Okay, so now let's apply the summation forces along the streamline which is equal to mass times acceleration, and that acceleration will be acceleration along the streamline as well. Okay, so summation of forces, then let's assume every force that's acting, or the direction is to the right, then that's positive, and to the left, then that's negative. Okay, so this is positive, then this one is negative. This pressure acting at the right side, that's negative, and the weight is also negative. Okay, so if we write that down, we have P dA minus P plus the differential pressure, should there be any, times dA minus the weight sine theta is equal to MAS. Now let's express this AS. We can express this as a function of position. So that's V dV all over ds. Now this is actually a work energy principle. If you recall that in our course in dynamics, that if we use this expression, A is equal to V dV all over ds, right? Summation forces is equal to mv dv over ds, then that's gonna be f ds is equal to mv dv, and this is actually a work, as if that's because f times the displacement along the force direction. Okay, so this is the work, and then this one is the, if you integrate this, you'll get the kinetic energy. That's mv squared all over 2. Okay, so this is now our expression. Now if we substitute this plus also, or we'll write it here, AS equal to V dV all over ds, and our weight is just simply equal to rho g times the volume. We're in this this volume is just simply rho g times the dA. This is dA, and let's say this is the length of this is ds. That's the differential length along the streamline. So dA times area times the length, ds. Now for the mass, we have rho times dA times ds. Again, rho v, that's the volume, and I guess we have everything right now, or I guess this one too. So for the sine theta is just simply z all over or better, if this is ds, we'll just convert this in terms of ds. This will be dz, then this will be dx. That's the differential length along the streamline, that's ds. Then this one will be dz, again refers to the differential length along the vertical direction, and this one the horizontal direction, which is x. Okay, so dz all over, okay, so sine theta dz all over ds. Okay, so now let's substitute. We have p dA minus p plus dp dA minus our weight, which is rho g dA times ds, is equal to our mass is rho dA times ds, and then our acceleration is v dv all over ds. Okay, so if you notice, each term we have the differential area, right? So we can divide both sides by dA, so this will be equal to 1, this will be equal to 1, this will be equal to 1. Okay, and we have this this is just simply the differential pressure, so just the delta P, or if we take the limit, then what we get is dP, except that we have to take into account this negative sign, so this is like P sub 2 minus P sub 1, so that's going to be negative dP minus rho g times ds, except that I guess this should be ds times sine theta. Okay, so times sine theta. Okay, so rho g times ds. Alright, I'll write it here. That's dz all over ds is equal to rho ds vdv over ds. Okay, so for furthermore, we can simplify. This is just equal to 1. Then this one is equal to 1. Therefore, that's minus dp minus rho g dz is equal to rho vdv. Okay, now if we try to bring this term into the left hand side, what we get is negative dp minus rho g dz and minus rho v dv is equal to 0. Therefore, since we have the negative sign throughout all the three terms, then we can divide both sides by negative 1, and that's just dp, right, plus rho g dz plus rho v dv is equal to 0. Okay, and let's divide both sides by 1 over rho, so that's dp all over rho, okay, plus g dz plus v dv is equal to 0. Okay, so this is now the differential equations along the streamline using the Newton's second law. However, although this is originally Newton's second law, I think this was derived actually by Euler, because he's the one who made the Euler's equation, and he made it more rigorous and more complete as compared to Newton. Okay, so now this is the differential equation along the streamline, or I mean the differential equation along the streamline. Which is known as the Euler's equation for fluid flow. And don't forget that we can also derive another expression, if we want to. We'll just have to apply the summation of forces along the normal direction, and then for the acceleration, you have to take into account or to substitute the value of acceleration that's toward, or that's along the normal axis. Okay, so the point here is that if we want to integrate this Euler's equation along the streamline, so let's say this is our streamline, and we want to integrate from point 1 to point 2. Right? So let's say if we want to integrate, then what we'll get is dp all over rho plus g dz plus v dv is equal to 0. Okay, so let's integrate this. Now, if we integrate this, if we can we'll assume that the density is constant. Okay, so assume density is constant. Otherwise, you have to express density as a function of pressure in order that you can solve this problem. So the simplest way is just to assume that the density is constant, or in other words, that the fluid is incompressible. Okay, so if this is constant, then what we get is just simply P by rho plus G times Z plus V squared all over 2, and that's going to be equal to the constant of integration. Okay, so what this means is that if we want to incorporate the limit, this is P1, let's say from point 1 to point 2, point 1 to point 2, then this will be delta P, this is delta Z, and then this will be delta V squared, right, is equal to 0. So in other words, we can see here that let's say P2 all over rho plus G Z2 plus the velocity at point 2 all over 2 is equal to the pressure at point 1 all over rho plus G times the elevation at point 1, and then plus the velocity at point 1 all over 2. Now this is actually what we call the Bernoulli's equation. Bernoulli's equation. Although this is named after Daniel Bernoulli, the derivations were actually carried out by Euler. Okay, so now let's interpret what this means. Okay, so let's write it again here. So we have P sub 1 over rho plus G Z sub 1 plus V sub 1 squared all over 2 is equal to the pressure all over 2. Okay, so what this means is that, let's check first the units. Now, what is the unit of pressure? The unit is Newton per meter squared divided by the unit of density, which is Newton per no, that's mass density. This should be kilograms per meter cube. Okay, so what is Newton? That's actually kilogram meter per second squared, right, divided by meter squared, and then this one kilogram per meter cube. So you would notice that this is kilogram in the numerator divided by the kg in the denominator, and what we get is actually a unit of this is meter. Okay, so that one, so this will be meter cube minus 1 m to the 1, then that's going to be meter squared per second squared. Okay, so this unit is actually a unit of energy. Okay, so how is that possible? Technically, this is a unit of specific energy. Specific energy. Okay, so it has to be specific energy. I mean, it has to be emphasized that it's a specific energy simply because the unit is joules per kg. Okay, so this m squared per s squared is just the same as joules per kg. So let's check m squared per s squared. So what is joules? That's just Newton meter, right? And then this one kg. Now let's break down this Newton. We have kilogram meters per second squared times meter all over kg, and we can cancel this kg since it's both in the numerator and denominator. Then finally what we get is m squared s squared. Okay, so what this means, what this equations means is that the total energy just says that the total energy is conserved, or the total energy contained in a given mass is the same at every point in its path of flow, right? Because if you, sorry, this should be p sub 2. So if you express this in terms of this one, okay, so it's just actually 0. So it just means that the total energy contained in a given mass is the same at every point in its path of flow. So if this is our path, then this, let's say this is our point 1 and point 2, and the energy at point 1, it says here, it's just the same as the energy contained in the in point 2. So that's the interpretation. So the question now is, how is it possible? How is it possible? Because we have a lot of terms, let's say at point 1, and then a lot of terms at point 2. So now let's discuss the different terms. Now, this one is referred to as the, we can call it a pressure energy, because it's the energy related to the pressure. Then this one, this is actually the potential energy. And this one, the v squared all over 2, that's actually related to the kinetic energy. Okay, that's actually the specific kinetic energy, because that's per unit mass. Okay, so it says here that we have the pressure energy, the potential energy, and then the kinetic energy. So that's present in point 1, and we'll also have in point 2, we'll also have pressure energy. We'll also have potential energy with respect to position or elevation, potential energy, and we also have kinetic energy. Okay, so it says here that the total energy, when you say total energy, that means that the sum of the three terms is what we call as the total energy. Then point 2 says here we have total energy. So therefore, what it means that the overall is the same, but the magnitude or the values of each term may vary. Okay, but if you sum it up, it must be, or it is the same as the total energy at point 2. Okay, so that's the meaning of this expression. Now, although this is the Bernoulli's equation, there are many expressions with regards to the units. For now, we use the units of energy, but we can also express this expression in terms of head form and pressure form. Okay, so for the head form, now let's divide both sides by this gravitational acceleration or constant, gravitational constant. So that's going to be P1 by rho g plus Z1 plus V1 squared over 2g is equal to, so the point 2, we have P sub 2 all over rho g plus Z sub 2 plus V velocity at point 2 all over 2g. Okay, so this expression is in terms of head form. So when I say head form, the unit is in meters. Okay, so how is that possible? Then let's check the units. So the pressure is Newton per meter squared, and we divide this by kilogram per meter cube times the G, which is 9, that's meters per second squared. And this is Newton, and we have Newton, so that cancels out. Now we're left with m squared, the 1 over m squared in the numerator, and 1 over m cubed in the denominator. Therefore, the unit will be in meters. Okay, so that's the expression in terms of head form. Now, with respect to terms, we call this one as the pressure head. And this one we call as the elevation head. Then this one, we call this as the velocity head. The sum of pressure head plus elevation head, that's what we call the piezometric head. And the sum of the three terms, this is what we call as the total head. Okay, now let's talk about the expression, Bernoulli's expression, in terms of pressure form. Okay, so in terms of pressure form, we'll start with this expression, the energy form. So what we want is the unit of pressure. So that means that we have to multiply both sides by this rho, by this density. So if we multiply that, we get P1 plus rho G Z1 plus rho V1 squared all over 2 is equal to P sub 2 plus rho G Z sub 2 plus rho V sub 2 squared all over 2. Okay, so in this expression, if we check the units, we get this one is in pascals, or Newton per meter squared, and this one, that's gonna be in pascals as well. So that's kilogram per meter cube times 9 meters per second squared times meter. Okay, so this is Newton, so that's Newton per meter squared. Okay, so if we use this form, we call this pressure form, and the unit is in pascals, or the equivalent in the English units. Now for the term, this one is called the, this is referred to as the static pressure. Then this one is referred to as the, okay, that's just rho G Z, so that rings a bell. And this is just simply the hydrostatic pressure. Hydrostatic pressure. And then this one is called the dynamic pressure. Dynamic pressure. Okay, and this, or we'll write it here, static plus dynamic pressure is called the total pressure. Total pressure, or stagnation pressure. Okay, so my interpretation actually is that for the static pressure, I used to think that because of the presence of the fluid, then of course there's going to be a pressure being exerted. So whether that fluid is in motion or not, there's going to be a pressure being exerted. Now, with respect to the elevations, then of course that will also vary, and that's because that's counted in this hydrostatic pressure with respect to the elevation. Because of the moving or the motion of the fluid, because for example this is your hand, and then because we are actually submerged in a fluid, and that's air. Now, because of the presence of the fluid, then there's going to be a force exerted on your surface or on your hand. But if the air is being blown, let's say there's a blower right beside my hand. Because of that force, let's say, so because of that motion of the fluid, then there's going to be an additional pressure. That's the dynamic pressure. And the sum of the static and the dynamic pressure is called the total pressure. Okay, so another one, before I forget, since we have expressed the Bernoulli in terms of energy and energy form, we have also expressed in terms of head form, and we have also expressed in terms of pressure form. Then in terms of head form, there's it's also common to use the graphical representation, or I guess I have to continue this in the next video. Okay, so we'll just continue this discussion in the next video.